Ladies and gentlemen, I'm in the transportation business. I design bionic legs that augment human physicality. As you can see, I'm wearing 2 bionic legs that I invented. 6 microprocessors, 24 sensors, and muscle tendon-like actuators. I'm basically a bunch of nuts and bolts from the knee down. But with Bionics, I'm freed from the shackles of disability. I can run, skip, hop, I can do whatever I want to do. And when I stop, the Bionics respond seamlessly. Thank you. Bionic researchers contemplate a future in which technology no longer comprises separate lifeless devices from our minds and bodies. A future in which our built world has been carefully integrated into our nature. A world in which what is biological and what is not, what is human and what is not, and what is nature and what is not will be forever blurred. You know, it's ironic that we understand today in this world synthetics more than biological constructs. With my colleague years ago, Bob Dennis, we invented a robot, a hybrid machine powered by living muscle tissue. And the machine that we called an actin-myosin machine swam through its own media comprised of oxygen and glucose to fuel the muscles. Now, our machine, because part of it was living, died after 48 hours. Because the science of organ maintenance had not yet been perfected, this occurred. But in the future, we will understand biologic constructs as well as today we understand synthetics. And in that future, when the architect designs and builds, she will say, this part of the machine, do I want to use a biological material or a synthetic material? Do I want to use skeletal muscle or shape memory alloy? Do I want to use skin or polymer? So in that world, that future world, hybrid machines will result, where like our actin-myosin machines that will not die, that will live on as part of the built environment, the built world, a new nature. That new nature will give us new bodies. From today, in which we live in a world where disability is commonplace, to a future world where disability is no more. Through advances in bionics, from seeing impairment that was talked about in the last lecture, to spinal cord lesion, to even severe depression, all these conditions that today, because of poor technologies, result in disabilities, will be systematically eliminated as we march throughout this century. And that the basic science and technology that will enable the elimination of disability will also enable human augmentation, or allowing a human being to have capabilities cognitively, sensorily, or physically that extend beyond what nature intended. To march towards this future, I recently established the Center for Extreme Bionics at MIT with colleagues Ed Boyden, Joe Jacobson, and Bob Langer. The mission of the center is to advance the fundamental science and technology that will enable the repair of humans across a broad spectrum of conditions affecting the brain and body. Now, human bionics explores this interplay between biological science and design. So a key question in bionics is, how do we work? How does the human work? By understanding the morphology and dynamics of a human, designers are better able to advance biologic or synthetic constructs that attach the body or implanted inside the body for the elimination of disability, or in some cases, for human augmentation. So today I want to tell you about how my legs work, an example of an assistive technology that has normalized my function. I can walk at normal speeds, normal amounts of energy levels, normal stress levels, and so forth. Then I'm going to tell you how that basic science has now informed an exoskeletal design that can actually augment a person with a normal physiology. So again, as we advance the science of human repair, that will enable us to augment humans in all kinds of different ways. So running on the microprocessors, the computers on my legs, is a biophysical model of how muscles work and how they're controlled by the spinal cord. So the motor, even though it's synthetic, is controlled in the same way as your spinal cord controls your biological muscle. So even though my legs are made of titanium and silicon and whatnot, they move as if they're made of biological tissue. So here's a engineering control design showing us a modeled muscle and tendon and what we believe to be the spinal cord reflexive loop. So that's actually running on chip in the device. So why do we care about how the biological limb does it? The reason is when you implement such a biophysical control, there's a remarkable emergent adaptive behavior. This gentleman was fit with this device just minutes before this video was shot. He wasn't asked to run, he just ran because he was inspired. And we didn't study running, we studied walking, and we embedded the fundamentals of walking on chip. But it turns out those fundamentals are also present in running. And that enabled this emergent behavior. Not only running, but as you could see, running up and down hills. So what about, that's how the machine works. What about the nervous system signals? Can we collect neural signals from muscles and nerves, for example, and have that drive the bionic? The answer is yes. And the architecture that we're using is that the neural signal modulates the gain or the sensitivity of that modeled reflex loop. So what's being run on my ankles is a positive force feedback. The greater the force borne on the ankle, the greater is the power that the ankle gives me. That's why when I run, it automatically adjusts. So what we do is we take the neural signal to modulate the sensitivity of that reflex. So when I don't fire my biological muscles, it's very insensitive. When I fire them, then it's very sensitive and I get lots of power correlated with force. So what are we doing to get the nerve signals? So we want to talk to nerves, we want to talk to muscles, and we want to do so bidirectionally. Not only getting movement intent out, but also to reflect sensory information from the device onto the nervous system. So we're exploiting a biological phenomena that's shown here. You see a muscle in M and a nerve in N. The nerve's been cut. But if you put a cut nerve next to a muscle that needs a nerve, the nerve will regenerate and attach to the muscle. This is a very robust phenomenon. And you can even take a cutaneous nerve next to muscle and the nerve will grow and attach to the muscle. So what we're learning is the peripheral nervous system is very, very flexible. And this is advantageous in developing a neural platform. So here shows an experiment where we put a transected nerve next to skin cells and muscle cells, and sure enough, the nerve grew and attached to those end organs. And then the body quickly vascularizes the cells that we put in. What we'll do is take signal from the muscle body, because the muscles naturally amplifies the signal. And for cutaneous feedback, we can stimulate through the cutaneous axons to give a person the sense of touch. This is what we're working on. What does it actually look like? We're microfabbing arrays. So this is a tube with many, many small tubes within a larger tube. And each tube has electrodes. We can sense descending commands from the spinal cord and send those out to a machine such as I'm wearing, so the person has volitional control of their limbs. In adjacent channels, we could stimulate and take sensory information from the bionic limb and stimulate to give a sense of touch or force or muscle state. So the nerve grows through these channels and then attaches to skin and muscle cells on the other side. So here just shows histology showing that we can in fact grow nerves through these channels. Shown here, red is the motor axons, green is sensory, and blue are Schwann cells. How do we get the information in and out of the body? Many people think the future of neural implants will employ wireless technology. But I'm not certain of that. I think the approach of wired is very, very compelling. Here is one wired approach. This is called osseointegration. You see on the left is a black shaft. That shaft is made of titanium That goes from outside the body through the skin membrane into the bone. And you can attach anything to that shaft, such as a prosthesis for a mechanical loading. So here you see a kitty cat that lost a hind limb, which is very common in our house pets. Maybe there's cancer or whatnot, and the animal loses a limb. So you can see the little prosthesis on the hind limb. That's direct skeletal loading. So what we're doing is actually making that shaft hollow. Guess why? To run wires in and out of the nerves and muscles to the bionic limb. So we're actually building little tiny bionic limbs for these animals. So this is the prosthesis that I want in the future. So that's the prosthetic story. How can we use these ideas to augment a person with a normal physiology? This is the most extraordinary patent that I've ever found. Years and years ago, I was at the US Patent Office, and I was digging through piles of patents, and I came across this patent. It was by an inventor that worked under a Tsar of Russia before communism. His name is Yagin. His goal was to augment the Russian army. And his proposal, his invention, was to strap these giant leaf springs in parallel to the leg and then try to clutch them in and out as he ran. As far as I know, this was never built, given the limited technology back then, but it's a very compelling idea. So there's been a lot of exoskeletal designs that are in series with the leg that essentially make the person taller. This is the power skip. Many of you have seen this technology. It was developed by folks in Germany years and years ago. Clearly, it augments jumping, if you're crazy enough. But it actually destabilizes the human, because the human's taller with these devices, and it interrupts the foot-ground interaction, which is always problematic for stability. Years ago, I designed this running shoe that has carbon composite springs in the sole. It stores a small amount of energy and decreases metabolic rate by a few %. With this shoe, you can run a marathon and cut about 8 minutes off your time, but it's nothing that exciting. But things get really exciting with a Yagin type of device that's in parallel with the leg, that runs up the leg. In 2014, my laboratory was the first to develop an exoskeleton that actually augments a person with a normal physiology. So these are essentially artificial calf muscles that are running the same algorithms as I'm using in these prostheses. So instead of the biological calf muscle adding all the power, the synthetic calf muscle is. So those muscles can exert less force and save the person energy and reduce stress. These exoskeletons are so augmentative that when you wear them just for 20 minutes, your own normal biological legs feel heavy and stupid. Interesting, huh? So this is just a graph showing that the device inputs a lot of mechanical power, shown in the upper left, and then the result of that input in mechanical power is a reduction in metabolic cost. And here's the same diagram. So again, we have modeled muscles and tendons and spinal reflexive running. That's kind of like a virtual muscle attached to the biological limb. We're also going up the leg and building devices that span the knee, that augment running. So we think that in the very near future, you'll walk down the street of your local town, and it'll be commonplace to see people wearing robots. Why? They may want to augment their running or walking, or they may have an injury and want to protect their knee or their hip for further joint degradation. So I'm going to finish my remarks with a discussion on new identities. This is Amy Mullins, the visionary Amy Mullins, on an early Cremaster film by Matthew Barney, showing this seamless integration between animal and human forms. As we go into this century and there's more and more bionic technology, human cognition, human sensory experience, human physicality can just be adapted by any individual. And through that type of bionic adaptation, an individual can just modulate their identity. So a future human will be able to sculpt not only their physicality, sensory experience, and cognition, but their very identity. The designer of the future will go inside and design himself. I've experienced this identity switching in my own life. So after my biological legs were amputated, I returned to mountain climbing. I lost my limbs mountain climbing to frostbite, and immediately after my limbs were amputated, I started climbing again. Initially, people said, "Oh, you're so courageous, but you're never going to climb as well that you achieved prior to the amputations." But in 12 short months, I not only came up to my previous climbing abilities, but went past those abilities and was climbing rock faces that no one else had ever climbed before, whether with biological or bionic legs. So at the beginning of that year, after my limbs were amputated, people said I was a crippled and a weak person. At the end of the year, I was a threat to my fellow climber. In fact, many of my climbing colleagues threatened to cut their own legs off to compete. Imagine that. So what do you see in this photo? Do you see a crippled, or do you see an extreme athlete? Do you see a weak person, or the potential of an augmented, transcendent human? What is my identity? I believe you know what I see. So because of inadequate technology, many of the conditions that you see here result in disability and a poorer quality of life than is sought. But disability can be overcome through technological innovation. I happen to have the minor condition that my biological limbs are amputated. But because of great bionic technology, I can do whatever I want to do. I can run, I can climb mountains. I'm not disabled at all. Now, if you remove the technology from my body, all I can do is crawl. But with bionics, I'm freed from the shackles of disability. So as we march into this century, systematically through innovation in bionics, we will eliminate disability after disability. And again, that fundamental science and technology that will enable the elimination of disability will also enable persons with quote-unquote normal physiologies to have an augmented experience. So in the future, indeed, we will see bionics that augment cognition, learning capacity, sensory experience, and physicality. So clearly, bionics has tremendous potential for humanity, but not without risk. In my view, we need to push on public policy as this ever-expanding augmentation technology emerges in this century, to further incentivize innovation, but also to mitigate unintended consequences of bionic platforms. It is not difficult to imagine a hard future of parents designing their future offsprings, of governments controlling the mood of their citizens, and many other brave new world outcomes. But I feel passionately that we, the people, have in our collective authority the power to eliminate disability in this century, while simultaneously adhering to those human values that we hold so dear, human diversity and individual freedoms. So thank you very much.